My name is Pennung Warnitchai. I'm a faculty member in the field of structural engineering. And Dr. Navid asked me to give a lecture on wind effects on the structures. But he gave me 1.5 hours, which is too short to explain into detail, but is long enough to give an overview. So I decided to make this presentation as an overview on wind effects on buildings and structures. Okay. If you have any question, you can stop me at any time. All right. And I think most of the presentation are basically focused on seismic design, earthquake response, and this is probably the only one that is not about earthquakes, just about wind. But we follow the same concept, performance-based design. We look at the real performance, the real behavior of the structure under the natural loading. I think in most of the view of engineers, the performance-based design, we focus on the structural side, the behavior of the structure. I think to do a proper performance-based design, you have to understand the loading side as well, the nature of loading. And for wind effects, the loading is quite complicated. Earthquake as well. So first, I think we have to discuss about wind. And when we talk about the wind resistant design, we look at strong wind that's produced by windstorm. Okay? This is a picture of important type of strong wind called typhoon. All right? Actually, it has many names, many different names. Typhoon, or in the US we call hurricane. In India or Bangladesh, this is called cyclone. Okay, but it means the same thing. It's a tropical cyclone with a relatively high wind velocity. About the surface wind velocity exceeds 120 km per hour would be called typhoon, hurricane, or cyclone. But maximum wind speed could reach 300 km per hour, which is very, very strong. Now another point is the size of cyclone can be very large. See in this picture is a satellite image. The size is around several hundred, about 300 km wide. It's a rotational flow, so it produces wind in tangential direction. Okay, and if you look at the cross section, it looks like this. This explains briefly about the mechanism that produce energy to the cyclone. Basically, it has to be originate over the surface of ocean, where we have supply of warm, moist air. The warm, moist air will be sucked to the higher altitude, and it will be cooled down. And it will be condensed into water vapors to water drop. The condensation process will release latent heat. Latent heat will be used to drive the rotational flow. Okay? So basically, it uses the warm air, moist air over the water surface as an energy source. As long as it stays on top of ocean surface, it can continue. But if it enters the dry land, when it enters the shoreline, then you have only dry air. then the cyclone will lose its energy. Okay, and over the land surface, the roughness is very high, so it will die out very, very fast. So basically, if it stays on top of the water, it can maintain its strength, but once it enters to the land, the strength will drop, and it cannot enter very far. So this is a picture showing where the cyclone or typhoon or hurricane originate, mostly in, of course, all of them in the ocean, but it will end in the land. All right, but not very far inland, mostly in the coastal zone. So, for example, take Australia. Inside will not be affected by typhoon, but along the coastal line, there are risks, and it's possible to be hit by the cyclone or typhoon. Okay, but in some countries are quite free from cyclone, like Indonesia, here, Malaysia. Some countries are very prone to cyclone, like Philippines, Vietnam, Bangladesh, and so on, and here, Florida. This is a picture for Thailand and Vietnam. You can see that comparing between Vietnam and Thailand. In the coastal zone of Vietnam, so many typhoons hitting the coastal line. Thailand, very low in number. Okay, it's come maybe every 20 years. But when it's cut through the southern part of Thailand, it can produce disaster. Like this case in Chumphon area, hit by typhoon Gay. We normally divide it into 5 scale, 1, 2, 3, 4, 5. From 1 is the weakest to the strongest, level 5. This is level 3. Okay. And I think about 5 years ago, we have the level 3 and level 4 level. Typhoon Nagis hit the Irrawaddy Delta of Myanmar. Normally, the cyclone or typhoon path is to go to India or to Bangladesh, but this one is follow not so normal path. It's turned to this way and then hit that zone. So it was a rare typhoon from Myanmar, but it was able to produce a lot of damage to the area. And it's actually caused a side effect we call storm surge. It raised the level of water, produced a flooding into the land. In this area that I visit, called Ajale village, in the delta zone, the water was rising up to his neck, that guy. But in some other village, it's above the head. So it's probably the most important factor that caused a large number of casualties in the area, not the wind velocity. That is the well-known type of strong wind. I'd like to show you another type called thunderstorm. Okay? It is very common here in Thailand, where you have kind of a dark cloud and very heavy, intense rainfall in some local area. The size of this windstorm is much smaller, not several hundred kilometers, but it's just several kilometers. Okay, it's a kind of local wind, and it's produce also lightning flash. So we can check the frequency of this windstorm by looking at the lightning flash like this. This is a satellite image showing the location of intensity of lightning flash. Okay, so we have this kind of thunderstorm more in Thailand, Cambodia, Vietnam, in Malaysia, in Indonesia, okay, and in other countries. But the people in Japan, for example, do not know about this thunderstorm. This is rare for them. All right, and this is a picture of the cloud. Cumulonimbus produce an intense rainfall, and it will bring down the air when we have an intense rainfall. And the air will spread out in a radial direction, okay, and then return back in a circulation route. Oh. So if you are here, you don't feel the wind because the air is coming down to your head together with the rain. If you are here, the wind just turns from vertical to horizontal, okay? And when wind velocity will be strongest. Now if you are here, it's already spread out, velocity will reduce before it returns back, okay? So the wind velocity are not uniformly distributed. It's very high somewhere near the center, but not at the center, and then it reduces. So if the structure happen to be here, then it can be subject to very high wind velocity. Now this is a picture showing the wind velocity profile. I mean, we plot how wind velocity vary with the height above the ground. Okay, for different type of terrain. This is a city center, this is a small town, this is open water. But this profile is for large scale wind, like cyclone. But for thunderstorm, which is small scale wind, it looks like this. It's different from this profile. But if you look at your design standard, design code, it will follow this black profile. Okay. No one mentioned about the red profile from thunderstorm. Basically, we still do not have design guidelines how to handle thunderstorm. The wind is strong near the surface. It's reached the maximum somewhere around 20 meters above the ground. Okay. It reduces when it's around 40 meters or higher above the ground. So it can produce a maximum effect to the structure like this. The structure that is large, not very tall, okay, about 10 to 40 meters high. Okay, these are the type of structure that will be most affected by the wind thunderstorm. Large billboards. I think you have many of these in your country. We have many here also in Thailand, in Bangkok, and many of them collapse by the effect of windstorm, basically by thunderstorm. Okay, and if a thunderstorm occurs here at AIT, and you go to Rangsit, which is about 10 kilometers away from here, you will not feel this strong windstorm. Okay, it's very high, intense wind in the local area. This is a tornado. I think very well known. You see many movies from Hollywood about this. This is the strongest type of wind, but the size is smallest. It's about 300 meter vortex. Okay, and it can move around 10 to 20 kilometers long. It can produce a wind speed up to 360 kilometers per hour, very high. It can lift the car like you see in the movies. Okay, this is a tornado funnel moving toward the city, Miami, but then it's changed its mind, turned to somewhere else. so the city was lucky. The map here shows where you can find tornado. So basically it is in the central US. Okay, so it's not our problem. Okay, so we are kind of free from this problem. We have some moderate level, but the tornado produced are not so strong. Okay, that is about wind. I moved into a new subject called aerodynamics, which will link between the wind and the force. Okay, how wind generates force, because the force is action to our structure. So this picture gives you a simplified idea. If we have a solid body in the wind stream, okay, the solid body will modify the wind flow around it, and due to the change in the wind flow stream around the solid body, it will create non-uniform pressure around the body, around the surface. Say if the body is, say if there is no wind, the pressure on all sides of this body will be equal. The net force produced on this body will be zero. Okay, but when we have the wind stream, the front side you have the increase in the pressure. The back side you have a reduction in the pressure. Okay, on the other side also some change in the pressure. So in here I use the arrow in mean increasing in the pressure. Arrow out from the surface mean decreasing in the pressure. Okay. And when you have a change in the pressure, non-uniform on front and back, it creates pushing force in the front, pulling force in the back. Okay, and not only front and back, also sideways, cross the direction. So basically, wind can produce a force not only in wind direction, but also in somewhere normal to the wind direction. Okay, and it also produces moment as well, because we have to integrate the effect of pressure around this body. Now, if you understand this concept, let me check some idea. Let me borrow this one. Say, this is a panel, okay? A billboard, for example, with a plane. If wind coming this way, the force will be this way, right? Now, let me change the question. If the panel is not perpendicular to the wind, what will be the direction of force on this panel? It will still be the direction along the wind or somewhere else. According to aerodynamic theory, the force is produced by the change in the pressure, front and back, and pressure is always normal to the panel. So even if the panel is inclined to the wind direction, the force will always normal to the panel. Okay? You always have the force perpendicular to the panel for this case. And this is a simple formula to calculate the wind load, which is appear in most design standards. We have a term looks complicated called velocity pressure. It's a 1/2 times mass density of air times the square of wind velocity. This is called velocity pressure. When this term have a unit of pressure, then you need to multiply by area to turn it into force. The area, it's difficult to use the area of the structure or of the object. So we normally simplify them into a so-called projected area. Okay, we create a plane perpendicular to wind direction. We project this structure into this plane. So the projected area of this structure is V times L. Okay, a simple frontal area. It's an area that wind will see the structure. And then we correct by a coefficient. This is called aerodynamic coefficient. We have drag force, CD, lift force, CL, and moment, CM. And for pressure, it's called CP. Okay? I hope you have seen this formula somewhere, sometime during your design. But the formula say that if the wind speed increased by factor of 2, the load increased by factor of 4. Okay? If wind speed increased by factor of 3, the load increased by factor of 9, because it's proportional to the square of wind velocity. All right? The load also depends on the area. If you have large area, you have high wind load. This is completely different from earthquake loading. Earthquake loading is proportional to the mass. Nothing to do with area, but wind load is proportional to the area of the subject. Okay? And aerodynamic coefficient, you can take it. There are many tables, many literature, many documents, and also in the design standard. But most of them are somewhere between 0.5, 0.3 to 2.0. Okay? That's the typical number. This is a pressure distribution for a circular cylinder when wind approaching this way. It says that in the front, when subject directly to wind, the pressure increase. But along the side, pressure turn into negative. I mean, it's below atmospheric pressure, reduced below atmospheric pressure. And on the back is negative, but small negative. On the side is large negative. Okay. So this provides information for engineers to understand what happened to our structure under the wind. These are buildings, small one. When the wind is coming this way, and when the roof is a kind of rather flat angle, the wind may produce additional pressure to the front, small reduction in pressure on the back, and a large reduction pressure on the roof. Okay, that is something important, because this arrow pointing out means the pressure reduced by a large amount. Before we have the wind, the pressure outside and inside are equal. So you don't have the load onto your roof except the gravity load of the roof itself. Now you have reduction on pressure outside, but inside you have atmospheric pressure. So basically you have a force pointing upward, okay, to the roof. Try to push it up. We call this suction. Okay? And this suction, if you are not designed for the suction, the roof can be damaged. It may be blown away by a strong wind, like this one. This is a picture of many houses damaged, mostly in a roof zone, roof damage by Hurricane George in Puerto Rico. Let's explain the mechanism. First, the wind produces negative pressure on the roof, and then somehow the doors or windows break, wind get inside, adding more pressure into internal, produce more uplift effect, okay, to the roof, destroy the roof, and then destroy the panel on the side. That's a mechanism that destroy many buildings by cyclone and by tornado. So you, in design of such system, you have to anchor down the roof system down to the column down to the foundation, lock them up to prevent this uplift effect. Okay. I'm sorry, because some parts are in time. Still have no time to correct all. This is kind of the wind load on the billboard. Okay. And to make it simple for the design engineers, these are wind load by the ministerial standard of Thailand. Is say that you can treat wind as a uniform pressure. Okay, we apply uniform pressure to the billboard. So, So if we have uniform pressure and we have two legs supporting this billboard, the load from the panel will be shared equally to these two legs. Okay, so and you can design the structure to resist the load. But in reality, the load may not be uniform. The actual pressure is very complicated. Sometimes it's heavy on one side, sometimes it's heavy on the other side. Okay? It's changed with the time. It's a dynamic pressure. So when it's heavy on one side, it may create more load on that side. And your supporting column may be subject to much higher load. Okay? Maybe your safety margin that provided by the code is not enough to handle this, and which may lead to a collapse like this. Okay? Now we are trying to correct. I already put it into the new standard, but still, many designers still do not understand this and continue with the normal practice. This is another effect which is normally not accounted for in many standards. In most regulations, we call this aerodynamic interference effect. Okay? You have one building built. Okay, when you construct this building, there is no nearby building. Later on, somebody else develop another project nearby and create maybe equally large building so close to your project, and it produces channeling effect. It can generate more suction. The loading completely changed by the impact of nearby structure. Okay, this can be a problem. Sometimes the building far upstream can produce a very strong impact to our building. And in some cases, a building downstream of the wind can also increase the load to our building. So this is very complicated issue. And this is a well-known case of this aerodynamic interference effect. It's a hyperbolic shaped cooling tower